All right, welcome everybody to today's webinar by the IEA SHC Solar Academy on the topic of current developments in thermal energy storage materials. This is a webinar by the IEA SHC Solar Academy and hosted by us, ISIS, the International Solar Energy Society. Before we start, a quick word on ISIS and who we are, because I can see many new participants are joining us on the webinar today. So ISIS, who are we? We are a UN accredited membership NGO founded in the 1950s and accredited with the UN since 1992. And we represent individual as well as corporate members from countries all around the world. We have a very strong mission, which is 100% renewable energy for all, used efficiently and wisely. And to that end, we offer a range of key activities to spread this mission. One of our key activities are our biannual congresses, which take place somewhere around the world. One is the Solar World Congress. The next one is going to be in 2025. We just came back from New Delhi in India for the Solar World Congress 2023. And the next conference that's coming up next year is Eurosun 2024. And I'm going to speak to that a bit more as well. We also have two key publications. You will certainly know Solar Energy Journal, which is one of the oldest and longest standing solar energy journals. And then in 2021, we added our fully open access Solar Energy Advances journal to that. We also obviously have online measures, such as the webinar you're listening into today, as well as online and offline education initiatives for young researchers. And we also work in the Department of Knowledge Sharing, for example, through measures such as infographics and our Solar Energy Museum. Now, as we get into the webinar, I want to have a quick word on the Q&A session. So we will first hear all of the presentations of the webinar today, and then we will have a cumulative Q&A session at the end. You can send in your questions using the chat, and you can start sending in your questions anytime throughout the webinar. So as you are listening to one of the presentations and you have a question that comes up for you, send it in the chat. Ideally, please indicate who the question is for, and please also keep it short and precise. And now it's my immense pleasure to introduce you to the moderator of today's webinar, Bärbel Epp. Bärbel is the founder and managing director of the German consultancy Solvico, and she's responsible for the international newsletter on the web portal solarthermalworld.org, where she reports exclusively about market and technology trends in the solar heating and cooling sector. So Bärbel, the floor is yours. Thank you very much.
Thank you, Arabella, for the nice introduction. It's a great pleasure for me to be here again. It's our last webinar of this year, but we will have already plans for next year, and we will continue with this series of webinars. Yeah, I want to share my screen and show you some details about the IEA Solar Heating and Cooling Program. Yes. Oops. Oh, well. Is it visible?
Yes, thank you.
Yes, perfect. Okay. Well, the IEA SHC program is a project-focused international research collaboration. You see on the world map here the colored countries on dark red, which are direct members, and the yellow or orange marked countries are members via sponsors. So we have a huge crowd of very dedicated experts on solar heating and cooling, more than 200 that work on 9 current solar projects, research collaborations that we have listed here. You know, among them is solar neighborhood planning, solar process heat, solar cooling for Sunbelt region. We have solar energy buildings, as we have here today about compact thermal energy storages is an important issue. We have solar district heating, solar hot water for 2030, and integrated lighting and life cycle analysis for SEH technology. So you see a wide range of topics. If you want to join one of these topics and join a task and work with them, you first have to check whether your country is an IEA SHC member, either directly, the red color, or orange via an organization. Then you can learn more about a task on the IEA SHC website. We have sub-pages for each of the tasks. This is how we call these research groups. And you can find on the task subpage the task manager. And then you contact the task manager and discuss your interest and your expertise, and they will inform you they have regular meetings and you can join their meetings. This is the procedure. The IEA SHC, very important to notice, we are not just publishing research-oriented results, but also there's a lot of training materials on our website, case studies, fact sheets, databases. We also have a lot of tools that were developed within the task work, and all is available under a sub-page which is called Publications. What else do we offer? I already mentioned the webinar series. It's a quarterly based webinar hosted by ISIS. We have different topics along the year. We also have on the YouTube channel a lot of videos with experts, and also all the previous Solar Academy recordings are available on our website. And also a nice option, we offer online trainings. That means on the request of an IEA SHC member country or member organization, we have particular trainings, either large scale or buildings or solar cooling or whatever interests you. The past trainings were in the Caribbean. We had China, West Africa, South Africa, and United Kingdom. Where to find more information? Obviously on the website. This is the blue IEASHC.org-publications is the very summary page where you find all the publications where you can filter under particular topics. You can follow us on social media, LinkedIn or X, and you will have the YouTube channel, which gives you a lot of videos. And if you have additional questions, please contact the Secretariat on your disposal at any time. Again, two very flagship reports that are regularly published by the program. One is the Solar Heat Worldwide report, which is published once a year in June. It's a buff 80-page report, the most comprehensive data gathering on solar heating and cooling application, market and technology development, quoted a lot by big organizations like IEA, and you find it free for download at the link which is giving in yellow below here. The semi-annual newsletter, which is called Solar Update, is published in June and in December, and it highlights particular, sometimes events or content from the tasks, but also administrative works like administrative issues like the new chair or new countries or whatever is important to mention. So this was my short introduction, and I would like to start now with our webinar today on current developments on thermal energy storages. It's a split webinar. You can always choose with our webinars between an early or an afternoon GMT time and an early GMT time on Thursday, whatever is convenient for your own time zone. And please also note, if you listen to the recording now, because you are already on Thursday, then please type in questions as well while we go over the presentations, because we will raise these questions then in the separated Q&A on Thursday as well. So, well, this is now a time to introduce the really chair of this task 67 on compact thermal energy storage, which is Wim van Helden. He is working with the IEA INTEC in Austria as a senior expert on solar energy storages, but he's also an independent consultant. He has two more hats. Wim is a board member of the European Technology and Innovation Platform on Renewable Heating and Cooling, and he's member of the Scientific Committee of IRES, the International Renewable Energy Conference that will take next week in Aachen, Germany. And he will take a few minutes to give us an introduction into the topic of compact thermal energy storage materials. So Wim, I'm looking forward to your presentation.
Thanks, Barbel, for the introduction. Indeed, I will show you a first introduction on the task 67, task 40, with the long title, Compact Thermal Energy Storage Materials Within Components Within Systems, before we dive into the deep with the three following presentations.
Wim?
I cannot see the full screen. Yes, that's strange.
Which screen do you see?
On your own presentation.
Okay.
We can only see half of your screen. Oh, no, it's...
Okay, then I have to go out and check in again.
Okay, 1 second.
Okay, then now it should be visible.
It's strange,
No.
it's still cut. We have never had that, Arabella.
No. So Wim, what happens is when you go to full screen mode, it zooms in on the presentation. So we have a zoomed version, so we can only read half of it.
Okay.
Can you zoom out manually?
And this way, if I swap the screen?
Same issue.
Okay, and I think I will stop PowerPoint completely. And then try it again. Yeah, if you can let me share it.
1 second.
It seems as if it is shared already now. Not sure.
1 second. Here you go. Now you can share again.
Okay.
Yeah, now that looks good. I think.
Okay.
Perfect.
Thank you, Wim.
I now got another menu showing the different possibilities for my screen.
Ah, yeah. Okay. Good.
So apologies for this delay. First, introductory slides on the task 67, task 40 on compact thermal energy storage materials within components within systems. It's a joint task, meaning that it's a collaboration between two programs of the IEA. One program is the Solar Heating and Cooling Program, and the other is the Energy Storage Program. And within the task, more than 60 experts from 14 countries collaborate together, working on the topic in different subtasks. We started in June 2021, and it's a 3-year task, meaning that we will end mid of next year. It's one task in a series of tasks that we already had on the topic of compact thermal energy storage materials, which started in 2010. So what is it all about? It's on compact thermal energy storage materials, meaning that we are looking into either phase change materials, PCM, like here, this cube of ice that is melting. It's a phase change in which a lot of energy can be stored, or thermochemical materials, which can be sorption materials or hydrates or redox reactions. What we are interested in with respect to the material is its characterization. So what are the properties of this material? How can we measure it? Its development. How can we improve the materials? How can we make it better for certain applications? And the testing of these materials in components. So what is the performance of a storage material when we have a heat exchanger connected to it or a chemical reactor? These are all topics and questions of the task. And the goals of these tasks is to work on understanding the factors that influence the storage density and the performance degradation of these C-test materials. Also want to be able to characterize the materials in such a way that it's reliable, that it's independent of who is doing the test, and it's reproducible. We would also like to have methods with which we can effectively determine the state of charge of a C-test storage unit. And the aim is also to have better knowledge on how to design optimized heat exchangers and reactors for C-test technologies. These are the goals, and our approach is working in subtasks and working also together. So we begin with the applications. In which application is a thermal storage material needed, and what are the boundary conditions for these applications? So the application boundary conditions ABC could be temperatures or powers or the number of cycles in which this application is used per year or per day. The contact with other materials like copper or stainless steel or plastic, and the mechanical conditions under which the material is being transported or stored. These boundary conditions are used to improve the storage materials themselves. So what we do is we add other components, or we tweak a little bit the molecular structure of the material in order to have better characteristics of this material. We also test the material's performance on a small scale then, and verify whether these tests are suited in order to have the proper qualities of the material, and also use the boundary conditions for component development. So one level higher, storing the material in a component and then charging and discharging it, and then testing whether the performance is the performance that we would need in a certain application. This material component interaction is also important in order to determine what are the factors that influence the lifetime of a storage material. And in the end, we would like to have a design process of the component that is optimized and that is ideally bringing us to a proper configuration with the properties of the component that are suited for the application. The task is structured around 5 subtasks. So one task on material characterization and the material database. The second task on the actual improvement of the C-test material. The third task on the state of charge determination for the component. The fourth task on the stability of phase change materials and thermochemical materials. And the fifth task on component level to determine the effective performance with innovative materials of these components. In the webinar, you will see and hear about 3 topics that are further deepened in this webinar. The first topic is on the question, how can we test material properties reliably and replicably? The second question is, how can we determine the state of charge, SOC, of a compact thermal storage material and component? And the third question that will be answered in the third part of the webinar is, which factors determine the stability of the storage material? So enjoy the webinar. If you have more questions, you can either contact me or Andreas Hauer, who is the task manager for the energy storage program of this task. Thanks and enjoy it.
Thank you, Wim. I think that was very important for us to get understand a bit the framework of your very complex task, because Wim manages, you saw a whole university of researchers with these 2 rows of subtasks and PCM and TCM oriented. We have learned these short forms now as well, phase change material and thermal chemical materials, which is a very important terms that will be used a lot. Thanks, Wim. Great. So we will go to the next speaker. We have Dr. Helena Navarro. She is senior research in chemical engineering at the University of Birmingham in the UK. She did her PhD at the University of Barcelona originally. Her research focuses on the development of thermal energy storage solutions from laboratory scale towards commercialization, both in academic and in industrial environment. This includes thermal and thermochemical energy storage materials. And the title of her presentation today is Round Robin Test on Thermal Conductivity and Thermal Diffusivity. This is a difficult word, diffusivity. Probably you can spell this much better than me. So the floor is yours, Helena.
So good morning, afternoon. everyone. So let me try to share my screen. So can you see the presentation?
Yes, but not in the presenter mode yet. Maybe it's a bit slow.
Yeah.
We will go to presenter mode.
Now?
Yes, now perfect. Yes.
I'm trying to. Oh, wait. No, now I think you cannot see it. Can you see?
Yeah, it works.
Okay. Yeah, it's moving. I see something different. Sorry.
Oh,
So
sometimes it's a bit slow in reacting your own screen as well, but looks good.
okay. So thank you again for your presentation, and thank you very much for all of you joining today to this webinar. So my talk is about one of the subtasks that we presented within the Energy Storage Technology Collaboration Program. So it's task 40, subtask A. And I would like to present the current status of this subtask, that it has been, the work done is through what it's called round robin test. So this is the outline of my presentation, and I will go through why we're organizing a round robin test on thermal conductivity and thermal diffusivity, and some of the steps that we have agreed among the partners during this process. So the material that we have been first testing is a phase change material. So the motivation. So one of the first steps to design a thermal energy storage system is to select which technology we are going to use. And that end up selecting a material that will store thermal energy in a temperature change, phase change, or chemical reaction. So that depends. But those materials have characteristic properties that will affect the performance of the system. So really it's crucial to determine in an accurate way the properties in the working temperature range. So here are some of the characteristics that are needed during the selection process. And besides, of course, that it's one of the main factors on selection, we're going to focus on thermal conductivity and thermal diffusivity, because it can be a selection parameters when we need materials that stores and releases heat in a specific time. So when we have these constraints, we really need accurate values for people to design the final system. So to measure thermal conductivity or thermal diffusivity of thermal energy storage materials, we can find different techniques and methods. Here on the left side, you can see the different techniques and with the temperature ranges that they cover and the thermal conductivity values that they cover. Some techniques are used mainly for insulators, so you can see these narrow bars, but other can measure highly conductive materials. So among all of these, you can see that LFA and TPS are the two more versatile methods. We're not going to go into details of these methods, but here I want to show you, this is from a review on your right side, that these are the techniques that are currently being used to measure thermal conductivity materials. So here you can see from in the solid form, liquid form, sensible heat storage materials, latent heat, and thermochemicals. So at the end, what I want to show is that there's a huge variety of techniques that it has been using transient and steady-state methods to measure thermal energy storage materials. So what does this mean? That currently it's quite difficult to have comparable results. So what we're trying to do now in this subtask is to assess the methods that it has been used through the different partners of this task, and to try to understand the associated uncertainties and how we can standardize protocols that will allow us to reproduce and compare thermal properties, thermal conductivity among the different laboratories. So to do that, what we can do is what it's called a round robin test. And we can describe it as an inter-laboratory test where we measure and analyze the results performed independently several times. So that aligns really quite well with the aim of this subtask, that is to develop standardized measurements procedures for thermal energy storage materials. And the subtask A1.1, what we do is focus on thermal conductivity, thermal diffusivity. But there are others for specific heat, for density, and for other properties that we have seen in previous slide that are important for selection. So the round robin test here you can see in this image consists of mainly 3 steps. So, and these steps are organized and designed using what is called minimum necessary information. So this will be in the form of tables that partners, laboratories will transfer just for communicating. Okay. So here we can see that we have an example is we have N partners. Okay. And the main 3 steps that we will carry out during the round robin test is to identify the general information, so collection of equipment or the criteria, to develop SOPs, so the protocols, the type of tests we are going to carry on, and then to measure, and the third and final to analyze. And this process can be done iteratively, so we can optimize our results. So we need to, at the end, have an idea of the precision and accuracy of our values. So if we move to analyze what we have been doing in subtask A1.1, here on the right top, you can see all the partners that they have participated. So the process can be summarized in this not so complicated called smart graph. So again, you can see that there are 3 steps. That is to design the round robin test, to measure through the different laboratories, and then to analyze the results. So in between, there is the transfer of information using what we call, or what we are going to define, these minimum information tables. So what we did at the beginning is to define which tables we are going to need to allow an optimized round robin test. That is, in our case, the participant information, equipment available, material that we are going to test, the SOP that we are going to follow, and the results and the analysis that will go around. So you can see that depending on which step we are going to use specific tables to transfer the data. Here. Okay, so here I just wanted to show you a little bit more detail what we are calling a minimum information table. So an explanation of each table. So for example, the main information that we are talking about in the participant table is the institution and the contact person to allow good communication. For the equipment, what we want is to have a detail and the most relevant information of that equipment that they are going to use. For example, model, manufacturer, which capabilities, that means in terms of which temperature ranges can be tested, which type of materials. And for the materials, beside that, I will show you which material we selected internally. We also try to capture the sample preparation because this is a quite source of uncertainties and error. One of the most tricky tables is the SOP. So it's the standard operation procedure. So which protocol test we are going to do. And that one is the one that we want at the end to be defined to use as a standard. And it's the one that it took more time and consensus, and it's still under development because the participants in this subtask have a quite number of pieces of equipment, different methods, different techniques, and different capabilities. And for the results, what we have is just what we collect is the number of samples we have been testing, how many repetitions, the average of the values calculated by each participant, temperature, and the uncertainties. So now I want to present a little bit more in detail all these steps, all these tables. So this is, for example, a summary of the data collected of the partners related to the different pieces of equipment. So here you can see that there's a variation of sample size from milligram to tens of grams, and different temperatures that can be tested. So people can go from some ambient to 1,000 degrees Celsius. Also, the test can be done in air, different protective gases. So here you can already see the many differences and sources of error due to a huge variety of pieces of equipment. So regarding the material, we selected a paraffin, a phase change material. This one melts around 53, 58, you can see here. And really we selected this from Merck because it can be easily purchased by all the participants. We selected others, but they were not available in all the countries. And it's important that all of us can get the same material. In some cases, when there was difficulties, what we did is to ship the materials from one laboratory to the other one. So besides buying the material, we had to agree on sample preparation. Okay, so because the different equipments have a different shape and need to be, it's depending on the equipment that they have. One of the issues that could happen is that the PCMs, solid microstructure and crystallinity, could be affected during the cooling rate. And because we need to mold and shape from the liquid state to the solid one to shape it to have the desired phase, we have to agree on the cooling rate we wanted to follow. So then we tried to establish two cooling protocols, one fast and another one slow. Here you can see the differences, one heating up to 70 to reach the liquid state and cool down to ambient. So we consider ambient temperature around 20 degrees from the lab, and the other one to cool it at a really slow cooling rate. So a little bit below the melting point that was 50 degrees. Just here to highlight that some of the participants noticed that they were having some cracks or some bubbles in the sample, so that could be also a source of error. So we try to track and to write down all the sources of error that could be affecting our results and our precision. So let me change. So yeah, talking about procedures, I would like to present the ones that I mentioned before, the LFA and the TPS, that are, those ones were the ones that more participants had it or have it. And the idea is just to agree on a suitable and kind of easy way to follow this procedure for everyone. So as a common ground, all the participants, independently of the equipment, were testing 3 different temperatures, 25, 40, and 50 degrees. For now, we have reasons to just measure in the solid phase because there's a few participants can do it in the liquid phase. And a minimum of 3 samples, all of us. And for the LFA, it was agreed specifically that for each temperature we were going to measure 5 times, so 5 shots of the laser. But we agreed on a minimum of 3 measurements per temperature and sample. So here in the bottom right of the slide, you can see an example of sample preparation. So they are using some molds to shape I think it's 12.7 millimeter disc. And here for TPS, what I would like to mainly highlight, and that although all the different TPS, the equipment, pieces of equipment that the participant had, they use the same method. They use different probes and they use then different sample size. But in all the cases, they need 2 halves to prepare 2 halves where the sensor goes in between. So you can see that here the variety of sample preparation that there was captured. So you have from 3D printed molds to others that are used, I think, for normal baking, or others manufactured with an aluminum case. So again, another source of error. So, and finally, this was also the last steps to start the round robin test. We had to agree on how we were going to present the results, how we were going to calculate the uncertainties of our measurements. So for calculating the uncertainties, we follow the ISO guide for uncertainties. Here you can have the reference. And first, we determine the standard uncertainties of our values by calculating the standard deviation of the mean of our values and divided by the square root, just following these equations. And just to say that in this case, it's just we calculated the uncertainty for the experimental values, but in some cases, according to this guide, we can add the uncertainties of what it's called combined uncertainties of other parts of the equipment. It could be, for example, thermocouples, but we didn't reach that point. If we calculate the standard uncertainty, the ones that you saw before, and we just finished that, we're having a probability of roughly 60% that the value is inside the normal distribution. So that means that almost one third of times the value will be outside. So what we did is to present the results in what it's called expanded uncertainty, that is calculated from the standard one by multiplying it by a coverage factor. Here you can see the table. So at k equal 2, that is the most common way to of expressing uncertainty of measurement and analysis results, we're having a confidence interval of 95%. That's a more robust way of presenting our results. So just also another note that this approach is just calculating the empirical or experimental uncertainty of the results. That could lead to precise results, but they can be far from the real one. And for that, what we should do, and it's one of the next steps, is just to have the uncertainty of the systematic error that comes from the equipment, that it's done through the use of standard materials. Okay, so I wanted to present here a summary of the challenges that we have encountered so far in terms of equipment, sample preparation, results analysis, that makes more difficult or can make more difficult to compare the results if we don't fully agree and assess them. So one of the main challenges that we're having in this, but also we see it as an opportunity, and we're keen on testing as much as pieces of equipment that participants have, is that we aim to understand how their different methods and techniques increase the variability and results. And here we're talking about the transient methods and steady state methods, but within completely different techniques. So that was quite a bit challenging, because it made us to prepare few standard operation procedures for each one of these ones. So another one was about the sample. So different sample size, how I present it gives different ways to prepare and shape your sample, but also different results in terms of bubble trap during the cooling rate, or different, we say cooling rate, yeah, because of bigger mass. So we are having far bigger, it's in some cases around tens of grams, that due to the paraffin that it has a low thermal conductivity, it takes longer to cool down. So it doesn't follow the same cooling rate that small samples. And this one is the step that we're currently analyzing a few results. And what we have seen is that we are still in the process of agreeing on how we're calculating the uncertainties, because I've seen that some partners have sent me different ways to calculate the uncertainties. So we are still in that part of the challenge. So the next steps that we want from this task is to analyze all the values measured. This is the next. This is going to be the next meeting that we have all the results. Sorry, and we're going to compare all the uncertainties, and we are trying to compare within the same technique, but also with different techniques. So we are trying to see how we can adjust our data and have a precise and accurate result. And so,
Helena, can you speed up a bit, because we are advancing in time? Thanks. Perfect.
Yeah, I'm almost there. So after doing all of this assessment, what we want to do is go for second round of round robin tests, adjusting with what we have learned from this previous test, and maybe in the future explore new materials. So PCMs, for example, in liquid state, or inorganic materials that we are testing just organics, and trying to also test thermochemical energy storage materials. So really thank you for your attention. I'm looking forward for the question and answer session.
Perfect, Helena. Thanks a lot. This showed very well how complicated round robin tests are, and how important they are also to get standard into material science. Thank you very much for giving us this insight. It was very excellent. So I have to introduce the next speaker. We will go through the presentations first, and we will gather the questions. Please type them in as you do right now, and we will have a Q&A at the end. So we have another doctor. It's this time Dr. Gerald Engelmeier. He is assistant professor at the Department of Civil and Mechanical Engineering at the Technical University of Denmark, and he received his PhD in 2019. His research focuses on compact thermal energy storage for flexible solar heating and cooling systems, including experimental development and demonstration. Gerald teaches in Denmark and Greenland, and has 10 years of research experience working in Denmark, China, and Austria after he graduated in as energy engineer in Austria. The title of his presentation today is State of Charge Determination Using Material Response in Compact Thermal Energy Storage. I'm looking forward to your presentation, Gerald.
Thank you, Bärbel. I will share my screen. All right, we are set to go.
Perfect, yes.
Well, I will talk about state of charge determination utilizing material response. And this is work results after 2 years, which are led by myself and by my colleague Peter Scheber from Natural Resources Canada. Why state of charge determination? So the idea is to enable integration of compact storage in interaction with advanced, you can also say predictive controls in energy systems. And to do it reliable, will potentially pave the way for flexible heating and cooling systems, which can also contribute to what management people would call reserve market access. Our definitions, which we made in this task, is what we would like to implement as a thermal battery, is a thermal storage with instantaneous charge determination, which means you do not rely on the measurement of heat flux. You can actually plug off the storage, you measure, and you instantaneously know what's going on. And we will utilize a response from a material bulk. However, the term or the parameter state of charge is a component level property. like when you buy an electrical battery, you also measure the state of charge of the entire item with different chemicals inside, for example. And it's defined as the heat content accumulated or at a specific time divided through the maximum capacity. We started with a survey. We had a look what is available in terms of measurement techniques. Well, quite a list for PCM and even a bigger list for TCM, thermochemical materials. So what we did is to reach out to all the partner institutions. We convinced 21 of them from 11 different countries to report their studies they have done in the past or currently. And then we had a different picture. We basically saw a focus for phase change materials on measuring the bulk temperature, which is the standard for labs in order to make models, for example, and a couple of investigations also in material labs on a smaller scale with the newer methodologies. It was vice versa for thermochemical materials, where you had a huge variety of investigations from the material labs, but only a few which are scaled up. So we can say that's a pilot storage where you try to investigate something. And just to highlight what it is, PCM, I mentioned temperature and pressure. And for thermochemical materials, it's mostly also temperature in combination with weighted pressure when we talk about sorption or thermogravimetric measurements, or simply to measure how much is in a vessel of a reactor. All right, after this step, we decided to make our own research classification for these rather new fields. First level is material bulk response. So basically, we measure with any new developed device a sensitivity across the state of charge. Second step, we build a pilot, like for the pilot labs, to identify the correlation of this signal from the material response to the actual heat content. And the third step in our classification is to understand or to define how can it be used in systems and what are the requirements to make the system work flexible. And in the next minutes, I will show you some exemplary proof of concepts from our institutes. It's not a complete list, but something to trigger some discussion. And I will start with material, then component, and then system level. First example is from the German Airspace Research Center. It's a storage pilot for sodium hydroxide. So for sodium nitrate for high temperature storage. And here we have an example where we have discharge at 290 degrees constantly. The melting temperature is a phase change material inside is 306 degrees. And you can then see from top to bottom that you have a signal of the electrodes, which are placed vertically. So again, it's a material level example where you can actually see that we have a proof of concept. It works. Of course, for a complete methodology, then you need some calibration work. Another example from Spain, from the University of Lleida. They created a setup where there is phase change material in a closed chamber, equipped with temperature measurement points and also pressure of a closed chamber. And then water by heat exchangers passing through heating and cooling the phase change material. And what was observed is basically that there is a clear correlation of temperature sensors and pressure. So it was as sensitive, but the pressure is a global parameter, while the temperature depends where you measure it. And also, if you know the density change of the air and the PCM inside here, then you can, that's indicated by this valley, clearly see when the phase change is actually going on. First, the solidification from liquid to solid, and then from solid to liquid again. The melting temperature here was 4 degrees. Going to thermochemical materials, we are switching to colleagues from FH Upper Austria. They developed a capacitive sensor applied to different zeolite material, and they showed us that the relative permittivity can be used as a sensitive signal to the water content of this zeolite. So when zeolite takes up water, it releases heat, and it needs heat to dry it again. And this is also a storage material. And yeah, they explained it for 3 different materials, all are sensitive. It's a promising approach. We stay in Austria. Experts from TU Vienna. They are working with higher temperature thermochemical reactions, and they have applied optical properties, UV reflectance. So here what we can see is basically 2 responses, the red line and the blue line. There we have a comparison of how does the response look with solid copper chlorides. There's a different spectrum in comparison to copper chloride and ammonia. And this ammonia, this is a certain, composite. And on the way, when you use it as a storage materials, you have different curves, and then you can track optically what is going on. Now, let's go one step further. Let's discuss what you can do when you have a complete system. And this system is built in Luzern, and it's a thermochemical reaction using aqueous sodium hydroxide, and by making the solution more concentrated, it requires heat, which can be stored in a tank, and you can apply it by diluting it with water via heat exchange, and then you release heat. And simply by knowing how much is remaining in the concentrated tank, you know what is the state of charge of your system. That's a quite easy example. It's not always that easy. One example from phase change materials from our lab at the TTU. So what we made here is a pilot for cold storage. We equipped a heat exchanger and material container with internal measurement, like 15 thermocouples we placed in here. And then during pilot testing with a lot of different inlet temperatures for both melting and solidification, we were able to find a correlation. And this is the graphical explanation for this correlation. The purpose is cooling, and the melting temperature is here 15 degrees Celsius. And which brings me to the next level, systems. When we have this model, we can, for example, you apply it for development of control algorithms for an entire server room cooling system in order to know how to actually place and apply cold storage in the right way, which is a novel system. And my final example goes to an actual product developed by Neothermal Energy Storage in Canada. And part of their development was to identify locations inside a phase change material storage with a melting temperature of 58 to know how to control it for different modes. And those modes are, for example, operation states like full cell charge, partial cell charge, and that's important for that type. It needs nucleation activation, so the PCM crystallize on demand, and this needs to be detected by selected locations. And it also tells the user or the system then when the cell is completely discharged and when you need to recharge it or activate another unit. Preliminary conclusions from our work. In 1 year we are ready, and then we publish a report or maybe a paper even. So it's the material bulk response we are aiming to investigate. The state of charge is, however, a component level property, including the insulation, the container, and also the heat exchanger. And it's a prerequisite for flexible system operation, in our opinion, to make it quick and reliable. For PCM, the development is basically we know how to measure the bulk temperature together with heat flux. that's maybe too complex for products, and we are therefore looking for novel techniques for mass application. And TCM, we have basically already tracking the absorbent content of sorption materials or measuring the mass of reactants in closed vessels. However, we need more non-intrusive techniques for large applications and for high temperature applications. Which brings me to the final statement. There is still a long way to go. We have first solutions, but we need more applied research to bring material science and system engineering together. Thank you very much.
They're right. I think we don't want to hear that there's still a long way to go. We have energy transition in front of us and we need storages extremely urgently. But I know that I think you gave us already some glance into what systems could look like and what complex questions will show up once you go to the system level. So thank you for that.
We already have solutions. Sorry, I want to say that.
Okay, you added that one. So that makes us again optimistic. So we come to our last speaker today, which is Angel Serrano, another doctor. You see that I think doctors are very frequent in this material research science. He's associated researcher at the Spanish research center CIS Energygan. He received his PhD in chemical and environmental engineering from the University of Castilla-La Mancha in Spain in 2018. And Angel holds expertise in developing phase change materials for energy storage across a wide temperature range. I'm excited about that, from 40 to 600 degrees, and he's actively involved in industrial, national, and European projects. The title of his presentation today is Stability Mapping with Examples of PCMs and TCMs. So please, Angel, I'm looking forward to your presentation.
Can you see now my screen?
Yes, but not yet in the presenter mode. But it might come because it's a bit, yeah, here we go.
Maybe now?
Yeah, perfect.
Okay, thank you for the introduction, Barbel. As you have mentioned, I will show you the stability mapping with some representative examples of PCMs and TCMs. Let's start by mentioning that the evaluation of the PCMs and the TCM stability is gaining relevance because the thermal energy storage systems based on latent heat and thermochemical heat are approaching the energy market. By 2030, these systems are expected to increase their durability, getting closer to the lifetime of systems based on sensible heat. Therefore, the stability evaluation of the main elements, in this case PCMs and the TCMs, is crucial. To define this material stability, let's initially focus on the main target of this stability, which is to achieve the test durability. And here in the test durability, two main elements appear: the time to maintain the performance and within established operational conditions. Therefore, we can use these two elements to define the PCM and TCM stability. A material is stable when it ensures consistent properties, avoiding decreasing the test system performance, and considering the operational conditions. So once we have a definition, what can we find in the literature related to this stability evaluation? Well, a few works have already made this initial effort to compile methodologies and present interesting approaches to address stability, but mainly focus on PCMs. Here are three examples that I consider relevant from 10 years ago, 5 years ago, and the last one even from this year. They have different approaches, but they all agree on one thing. There is no common standard or guideline for assessing the stability of these types of materials. Then, how do we perform this evaluation? As I initially mentioned, the application approach focuses only on properties affecting the test performance and testing within defined operational conditions. However, in the early stages of material development, this application may not be clear or defined. Therefore, in these early stages, we can focus on phenomena inherent to the material, such as degradation or sublimation temperature. As we define the application, we can incorporate new elements, such as the environment or operating conditions, for example, during the thermal cycle. And finally, we can even consider elements related to the system integration. For example, compatibility with heat transfer fluid or compatibility with heat exchangers. Hence, the application focus brings into play both operational conditions and external agents affecting the PCM and the TCM. To clarify how this evaluation can be done, I'm going to show you 5 representative cases, 3 for PCMs and 2 for TCMs, with different approaches when assessing the stability. Due to the limited time, some of these cases are explained in more detail in the annex attached to this presentation, but at least I would like to mention their main singularity. We start with a case from Fraunhofer focused on assessing and understanding the aging of erythritol, which is a sugar alcohol. This is a common approach when starting the stability assessment of a new material. On the top table, you can see the 4 main parameters defining the stability test: testing conditions, properties to follow the stability, testing device, and techniques to understand the observations. To give you a brief background about the materials, sugar alcohols like erythritol are solid liquid PCMs with very high latent heat at medium temperature, but with some challenges, overall related with crystallization and polymorphism. For example, erythritol has a stable phase at 120 Celsius degrees and a metastable phase at 106 Celsius degrees. With this in mind, in this case, they perform aging test by subjecting the material to temperatures 10, 20, and 30 degrees above its melting point. In addition to the change of color, as it is evident in the picture, the stability was evaluated by monitoring the latent heat and melting temperatures over the time. Also, some complementary techniques, such as attenuated total reflection spectroscopy and Raman spectroscopy, were used to assess this degradation. In the graph on the right, we can see, just as an example, the detection frequencies of the stable phase in green and the metastable phase in dark blue for erythritol, as well as when there was no crystallization in light blue for different aging temperatures over the time. They conclude that increasing aging temperature and time increases the probability of metastable phase, reducing the melting point and also decreasing the enthalpy of fusion. This is a basic example of the evaluation of stability and understanding the reasons behind this. Let's move now to a similar approach, but in this case applied to solid-solid PCMs, and more specifically to organic plastic crystals evaluated at CIC energy. Briefly, organic plastic crystals are highly energetic solid-solid PCMs with a transition from a low-temperature crystal phase to a high-temperature plastic phase. In this transition, they are breaking hydrogen bonds, and that's why their latent heat is high. They are very simple molecules with different numbers of hydroxyl groups, which provide quite different transition temperature. 2 of the main representative cases are pentaglycerine, PG, with 3 hydroxyl groups and a transition temperature of 80 Celsius degrees, and pentaerythritol with 4 hydroxyl groups, a transition temperature of around 190 Celsius degrees, and a latent heat up to 300 joules per gram. One of the main advantages of these materials is that we can combine them to continuously adjust their transition temperature. And in this case, we test one of these binary combination of PE-PG with an adjusted transition temperature at around 150 Celsius degrees. As in the previous case with sugar alcohols, the first thing to evaluate is the material stability when it is subjected to temperatures beyond its transition temperature. Here we use a thermogravimetric analysis to follow the mass loss, the blue line, with respect to the temperature, which is the red line. And it is evident from the graph that there is mass loss within the expected working temperature of the material. For the evaluation of the condensed material, we conclude that the binary system is sublimating in the plastic phase. Thanks to this initial assessment, we can propose solutions that mitigate or even eliminate this potential stability issue. For instance, through the use of external elements such as coatings. As an example, coatings with low vapor permeability can avoid these problems related with sublimation. In this case, we test binary combination in a closed system, subjecting the material to 150 thermal cycles between 120 to 200 Celsius degrees. And as we can see on the graph, their thermal properties evaluated in a TSC are not affected by the thermal cycling after 150 cycles. Therefore, we are able to mitigate this initial sublimation working in a closed system. To finish with PCMs, we have now a case from TMAT focusing on fatty acids. The main singularity here is that they use this initial stability evaluation to design lifetime models and to predict the PCM's long-term behavior. You can find more information in the annex attached to this presentation because it is a really interesting approach for the evaluation of the degradation. Now let's shift our focus to thermochemical materials, TCMs, where there are fewer reported cases of the stability evaluation compared to PCMs. Here is a case from the National Institute of Chemistry in Slovenia. They use the sorption processes of water vapor in a zeolite to store the energy. As a brief explanation, under the influence of a heat supply, the water is dissolved from the zeolite in an endothermic process, corresponding to the charging of the storage material. On the contrary, when the water is absorbed onto the zeolite, the heat is released in an exothermic process, achieving the discharging of the material. In this specific case, they are proposing the use of a commercial granulated binder-free zeolite as the absorbent material. The water absorption capacity of binder-free zeolites is higher than that of zeolites containing binders. However, the main drawback is their high desorption temperature, in this case 140 Celsius degrees. This high desorption temperature can be reduced by modifying the hydrophilicity of the zeolite. And in this case, is exactly what they are trying by applying different chemical treatments. In addition to this target, they are also evaluating the cyclic hydrothermal stability of the zeolites. So let's focus on this point. For this assessment, the samples were exposed to 20 absorption-desorption cycles between temperature of 40 Celsius degrees to 140 Celsius degrees at a constant water vapor pressure. At the end, the stability is evaluated by comparing the water uptakes of the samples at a specific temperature and vapor pressure before and after cycling. Apart from the results, the differences in assessing the stability of PCM and a TCM are evident. Here, in addition to the temperature, the pressure is a key factor to control, especially in systems involving gases or vapors. In addition, the number of cycles usually performed is significantly lower than in the case of the PCMs, where it is common to reach more than 1,000 thermal cycles during the stability assessment. Finally, this is the last example of TCM that you can see in detail in the annex, carried out by the Curtin University in Australia. In this case, it is not absorption-desorption, but it is a decomposition carbonation reaction with metal carbonates involving carbon dioxide. Temperature here reached more than 1,000 Celsius degrees, and the evaluation of the stability is performed at a constant temperature by changing the pressure of carbon dioxide in the system. It is a very interesting case where they even deal with sintering problems by doping with nickel particles. As you have seen, the variety of approaches and techniques for assessing the stability of these materials is extensive. It is necessary to have a set of recommendations that at least allow us to make some comparisons between the materials of the same family. In subtask D, we are mapping the potential degradation mechanisms for each type of PCM and TCM, including degradation factors and their effect on the material. At the end, the identification of these elements will allow for more efficient stability testing, long-term prediction, and more accurate problem-solving strategies. This is all from our side. I recommend you to download the presentation and to check the details in the annex for each representative case.
Thank you very much, Angel. Very interesting indeed that you went through PCM and TCM at higher temperatures. Yeah, we have a number of questions and we will start straight in the Q&A because of limited time. And we will go from the more general questions. I invite the others also to make their videos on again, and we will have questions to different speakers. We will start with Wim with the more general questions. There was one which was saying that what is still in macro scale and what is still in pilot stage. So can you give a bit of a rough idea of what is already available at normal sizes in terms of compact storages and what is still in the very pilot stage?
Yes, yeah, indeed. There's a number of materials already on the market, especially PCM materials. They are in a wide variety available from industries. One example is a storage for hot water that is based on sodium acetate trihydrate from the company SunAmp, which is on the market. It's a PCM based storage. And another example is the zeolite dishwasher that uses the zeolite in order to have a higher efficiency when dishwashing at home. So these are really mass market products, just to give two examples.
Okay. We have an interesting comment as well that came in while Angel presented, and I want to give it first to Angel, but maybe Wim, you can also comment on that. It says, where are the results of all the testing to determine the champions of PCM and TCM? It will save us a lot of time if the best materials is selected and just generated and used. I think that is a very straightforward comment. Why do you do so much research just to choose the champions? So we start Angel and then Wim, or if somebody else wants to comment on that, please. Angel?
Sorry, I didn't understand the question. Can you repeat?
Oh, okay. Well, the idea is, where are the champions? Why do you do so much testing? Why don't you just choose the best PCM and TCMs and go forward with them developing systems?
Thank you, Barbara. It is a good question, but the real answer is that there is no champion. It depends on the application. We cannot say that one PCM or one TCM is the best, because we need to take into account the application. And when I say the application, it is not only the properties of the material, you need to consider also the cost. Maybe the solutions that you want to apply to solve some stability problems is useful for one application because your material can be more expensive, but it is not fitting another application. So there is no direct answer, and there is overall no direct champions of a PCM or a TCM.
So anybody else sees champions? Or no more comments? Yeah, Gerald?
I mean, I see an importance to investigate also the interaction between the material and metals like heat exchangers. That's them for specific application. And yes, maybe it's there are some temperature areas when I talk about PCM, especially, which are well known of the materials, but there are also other temperature areas. I'm thinking about industry applications where we have quite a lot to do, and also to develop materials and to test them simultaneously. Okay, good. Wim, do you want to comment on that, or?
Yeah, I guess that it's not our task to find champions. It's our task to develop procedures and methods with which champions can be identified depending on the application. And we see also that in our work, that from time to time there's a group that detaches from us and finds and uses their champion, their personal champion, in order to work on prototypes and work on new products. And so. Okay. We make the basis, the test methods and the procedures and the ways to improve the materials and improve the components, and then we'll take this and
they use it and commercialize it. Okay. So Helena, we have some questions regarding your research work in round-robin test. Does your current research task considers the analysis of phase change materials with nanoparticles, and why do we not focus more on nanoparticles to store energy?
Okay, what we're trying to really do with this task, besides focus on that, because we are working with thermal energy storage materials, is to have at the end protocol to test any material. So we start with a material that it's gonna add difficulties because adding nanoparticles, what it's making is a more challenging study of the materials because of stability issues, because of nanoparticle size, agglomeration, stability. So that the idea that we selected a material that it's really standard, it's stable in the whole working temperature range, we can cycle many times, just to, at the end, to have a protocol for testing thermal energy storage materials. So that's the reason we didn't move to nanoparticles. We are complicating our lives unnecessarily.
Okay. Well, fair enough. And we were asked about which techniques have been used to estimate uncertainties in you were talking about your uncertainties.
We follow the guide for uncertainty, so it's a statistical analysis of our values. So for now, that as I mentioned, we were focusing on the ones from our measurement, our lab, so the ones that they are not systematic, but then we will move also for the ones that they come from the equipment. But this guide is widely available. It's quite useful.
We have actually another challenging question here. Somebody says, for beginners, if somebody is interested in getting more into material research on storage tanks and is not advanced yet, can you recommend any book or standard sort of, well, whatever source where to train first? This is what we get here as a question. Difficult. Maybe we have to give this in a written answer as well afterwards, or you have a...
I don't know it by heart now, the publication, but there's a number of publications that are reviewing what has been done on research and development for thermal energy storage, also for compact. And also previous tasks have produced publications in which there could be gained a first overview of what is possible.
Mm-hmm. I think so too. Getting back into the task, say again, the first number of the storage tank task was what? 30, you mentioned
it was task 2442.
24 and 42. So all material is still available on the website. If you go under projects and you just search for the previous task, it's not so specialized and there might be some more accessible publications. Very good idea, yes. Okay, then we have a question here for Gerald. How is nowadays the economic feasibility of including sensors for characterizing the state of charge of thermal energy storage materials, engineering applications, for example, solar air cooling? Very specific.
It's a very specific question, but I will give a very general answer.
Oh, okay.
I mean, solar air cooling is indeed interesting when you have air as heat transfer fluid, and you can definitely integrate also storage into these systems at maybe even higher temperatures. I worked a little bit with solar air collectors before. The question was cooling, I'm sorry. But generally, sensors, if you make a pilot, are expensive. And what we try, once we identify the suitable measurement techniques, to actually make pilots, to understand what is important in terms of sensibility and sensor signal. And I have the vision as a researcher that there will be technologies for different materials which can be quite cheap in mass production. But there is no answer yet, but I can also say it's a very exciting field.
Mm-hmm. Okay. Another question where I don't really know whom to address it to. Could you tell me some suggestions of PCM materials for solar drying of fruits and that are not costly for allowing continuous drying processes during night? Silence. An application for your... I think drying is 50 degree or 40 degree or something. So it PCMs, Gerald, on this level, 40 to 60 degree.
I mean, when you go into drying process, I would first say PCM is interesting, but maybe it's wise to also look into sorption materials to accelerate drying processes. So something you can couple with solar air collectors. where you can dry sorption material and perhaps to enable continuous drying processes via sorption containers, with example given silica gel or zeolite. Personally, I would first think about such a solution.
Okay, good. Angel, we have another question for you. How feasible would it be extensive use of coatings for mitigating supplementation of plastic crystals used in engineering applications?
Okay, again, it is a good question. To develop these coatings is a real challenge. Why it is a challenge? These plastic crystals are not compatible with water, which is one of the main solvents when you want to develop a coating. We have to take into account the volume change of these PCMs. It is true that now we have a solid, so the volume change is lower than the solid liquid PCMs, but still you have certain change. You need also a low vapor permeability, and the key parameter. You need a low price and a way to apply this coating, which is scalable, to be possible to do it in industrial scale. So it is a challenge, but if we take all these parameters from the beginning, from the design of the coating, it is possible. It's exactly what we are trying to develop these kind of solutions, taking into account all these restrictions of limitations from the beginning.
Okay, good. Thank you very much. Helena, another specific question to you. Which are the encapsulated methods considered in the testing of PCM?
I don't know if I understand properly. So the PCM, sometimes they are used in some applications by encapsulating them, because when they are in the liquid phase, sometimes it's difficult to handle, or they react with can react or leak from the materials or the surroundings. And there are different encapsulating methods, really depending on the nature of the PCM. So if it's organic, inorganic, and also in the working temperature range. So if we are talking about buildings, then we can use polymers to encapsulate. That one is well studied, and there is plenty of information in the literature, and there are even commercial products. But then for high temperature, you cannot use polymers, and then you move to use inorganic materials or metals, so alloys for that. But it's really depending. I think we are always talking that it depends on the application. So thermal energy storage has it can be used widely, but it's really application dependent.
Okay. How about stability issues? Did you look into stabilities in your round robin test, or was this an issue in your testing?
No, we really selected a material that it's completely stable and it can be cycled. That's one of the reasons that we didn't use or the materials like inorganic salts, that sometimes they have supercooling and they are more tricky to test.
So does anybody has other experiences with stability? Because we have somebody asking here for stability issues in PCM and TCM.
But what is exactly the question, Barbara?
No, whether you have experiences with, I think somebody's doubting whether they are really stable PCM and TCMs. Now, Helena said that they have only chosen sort of materials which are stable, but I think there are others maybe that show degradation.
When we try to determine this degradation of the PCMs, we use extreme conditions. For example, we use temperatures that usually are not reached in the application, but we need to force the system to detect this degradation mechanism. So maybe during most of the PCMs or TCMs that we are talking about these stability problems, in the final application is not going to be a problem, but we need to know if it is going to be the problem, if it is going to suffer this degradation overall, to predict in the long term. So there are a lot of options without any stability problem, but we are forcing the system.
Okay, thank you. I think we have one question where I'm not sure whether we have an expert on this call, and this concerns material that are used in thermal masses in buildings. The question is, we are interested in producing simple solar heat grabbers to use in existing homes. Are there materials that could be used that are better absorber materials out there in the heat side of a passive design, like in terms of lightweight and thermomass materials? I mean, I think they talk about activating thermal masses in buildings, and they ask you as material experts whether you have a recommendation from your experiences with materials on these low temperatures.
I know that say some 10, 15 years ago, there were some manufacturers of sealing elements that were used in order to assist the heating and the cooling stability of offices. So that there was a suspended sealing system in which there were mats of PCM hanging, which took care of an increase of the thermal mass of these offices.
Mm-hmm.
So I guess that there are products on the market for that. And the PCMs that they used, I think they were organic phase change materials.
Oh, okay. So you remember that one, good. Okay, well, I think we went through all the questions. Thank you very much for this engaged discussion, and thanks to the audience for the very many interesting questions that have challenged our experts. And I will get back to Arabella for the final words.
Thank you very much to all the speakers. Can you still hear me?
Yes.
Okay,
yeah.
Had to change headset in the meantime. Good. Well, thank you for taking the time to answer all of the questions. I'm going to close out the webinar now with a few general announcements. And that is that one of the regular questions we receive is, what about webinar recordings and presentations? Yes, the webinar is being recorded, and yes, you can receive all the presentations that you saw today. They will be uploaded to both the IEA SHC Solar Academy homepage as well as the ISIS homepage in a few days. So just be a bit patient, and then you will have both of that. For any ISIS members on the call, remember you have unlimited access to all past webinars, including the one of today, and the presentations in the ISIS members area. And then, hold on, finalmente, an announcement for 2024, because the year is coming to a close rather soon. ISIS and the IEA SHC are going to have our next joint conference, and that is the International Conference on Sustainable and Solar Energy for Buildings and Industry. You may know Eurosun as a conference. We've done it for quite a while. We first started in 1996. And next year, for Eurosun 2024, we will be going to Limassol in Cyprus, and that's going to be the last week in August. So an ideal opportunity for you to share your work, but also have a holiday on a very nice island. So this is my save the date for you. We are going to launch the call for papers rather soon. Just be on the lookout on the ISIS and IEA SHC homepages, and I hope to see many of you there. And then, if any of you wanted to share feedback with us, send an email to public.relations@isis.org. You find us on all the usual social media channels, and I'm happy to welcome all of you on the next webinar. Bye, everybody.
Bye-bye.
Bye.
Bye.